Hello everyone, welcome to the Exploring Technologies. In this video, I will explain about the Wavele Scattering Transform for signals and images. So let me show you the contents first, which I'm going to cover in this video lecture. First, I will introduce the topic Wavele Scattering Transform. Then I will show you that how you can compute the coefficients for one-dimensional signal. After that, I will talk about the similarity between the CNN and the Wavele scattering network, and how one can use the scattering coefficients as feature vector. Then I will talk about the Wavele scattering transform for two-dimensional signals, images, and in the last I will talk about the implementation in MATLAB for Wavele scattering transform for both 1D and 2D signals. And I will explain the MATLAB code also. So let me go ahead. But before going ahead, I recommend you to watch my following previous video, and that is an introduction to the wavelet theory and its application. So if you go through this video, you will have the exposure to the basic theory of the wavelet transform. So if you go through this, you will be able to understand this current video in better way. So link is given in this description, so you can watch this video. And now come to the Wavele scattering transform. So Wavele scattering transform was first proposed by the Stephen Mallet in 2012. This transform uses the wavelet function psi t and the low-pass scaling function phi t to generate the low variance representation of real valued signal ft. The wavelet time scattering yields a translation in variant representation of the input signal ft without sacrificing its class discriminability. The scattering coefficients obtained at different labels can be used as feature vectors and can be utilized by a classifier for the classification task. Now let's come to that how we can compute the scattering coefficients for one-dimensional signal. So at label 0, the low frequency scattering coefficients are calculated by simple convolution of the signal f with the scaling function phi t, and that is represented by this equation. And at label 1, the signal f is convolved with the wavelet functions at different scales. Wavelets of different frequencies, let's say psi 11, psi 12, psi 13, and other. That depends on that how many wavelets we choose for computing these coefficients. So here you can see that f convolved with the psi 11, f convolved with the psi 12, and so on. This is just similar to what we find in the continuous wavelet transform CWT. So these coefficients are known as the scalogram coefficients or simply the wavelet coefficients. Then a nonlinear operation, the modulus is applied on these coefficients. So we find the modulus of all these coefficients. And then all these coefficients are, after modulus operation, they are convolved with the scaling function phi t to get the scattering coefficients at label 1 as shown by these equations. Okay, so here you can see that the first wavelet coefficients are found, then we take modulus operation, and then they are convolved with the scaling function. So this is done for all wavelet coefficients. So these coefficients are known as the scattering coefficients. At label 2, the wavelet coefficients obtained in the label 1 are further convolved with the wavelet functions at different scales. So here at the label 2, again we are taking wavelets of different frequencies and we are using those wavelet functions for the convolution. And then we go for modulus operation. So these are the wavelet coefficients which are obtained in the label 1, f convolution psi 11, f convolution psi 12, f convolution psi 13, and so on. So these wavelet coefficients are further convolved with these wavelet functions psi 21, psi 22, and psi 23, like that. So here in this equation you can see that these are the wavelet coefficients obtained at label 1. They are further convolved with the wavelets of different frequencies psi 1, psi 21, psi 22, psi 23, like that. And then we find the modulus of these coefficients, you can see. And this operation is done for all the wavelet coefficients which we have obtained at the label 1. So these are this is the operation for f convolution psi 11, F convolution psi 1 1. So these all coefficients are convolved with psi 2 1, psi 2 2 and psi 2 3. So this convolution is done for another set of the coefficients, F convolution psi 1 2, which were obtained at the label 1. So again they are convolved with psi 2 1, psi 2 2, psi 2 3 and so on. And this was the third set, F convolution psi 1 3, obtained in the first label. So this is also convolved with psi 2 1, psi 2 2 and 2 3. So this is done for all coefficients which are obtained in the label 1. And now these all coefficients then convolve with a scaling function to get the scattering coefficients. So I'm just talking about this. So F convolution psi 1 1, then further convolved with the psi 2 1. So these are wavelet coefficients, and then they are further convolved with the scaling function, and then we take the modulus operation. So this is done for all wavelet coefficients. Similarly, this is for this second set, this one, and this is for this third set, this one, and this is done for all other remaining wavelet coefficients. So this is how we get all these scattering coefficients at level 2. Here node is expanding actually. So this operation you can understand in better way with this tree diagram. So here you have this input signal. So at level 0 you just go for the convolution with the scaling function. So these are the scattering coefficients at the level 0. After that, which I have explained, that F is convolved with the wavelets of the different frequencies. I mean psi 1 1, psi 1 2, psi 1 3 and so on. Let's say I'm taking n number of wavelets, and then we find the modulus operation, you can see, for all these coefficients. And after this computation we convolve all these wavelet coefficients with the scaling functions. Here you can see, so they are convolved with the scaling function. So these all coefficients thus obtained are scattering coefficients at level 1. And after that we take these wavelet coefficients and we further convolve them with the wavelets of different frequencies again. And then we take the modulus operation also like that. And then we convolve all these coefficients with the scaling function. Here you can see, right? So these are the scattering coefficients which are obtained at the level 2. So here I have just shown one node, okay, this node. So this node is expanded in these coefficients, but to find the coefficients at level 2, the same operation is done for this set of wavelet coefficients, and for this, and for all n number of coefficient sets we have to do this same operation. And if you want to go further, then again you convolve these wavelet coefficients further with the wavelets of different frequencies at level 3. So these wavelet coefficients are further convolved with the wavelets at third level. So psi 3 1, psi 3 2, psi 3 3, like that. So I mean this is similar operation which is performed at every node. So here you can see that this tree is expanding. So every node is expanding in n number of set of coefficients. So obviously it is computation hungry. So later I will show you that for signals and images we generally do not go beyond third and second level of coefficients. It is sufficient to compute L equal to 0, L equal to 1 and L equal to 2 for most of the signals and images. And now come to the similarity between the CNN, that is a convolutional neural network, and the Wavele scattering network. So just consider this CNN model. So in CNN we have several layers, layer 1, 2 and up to the layer n, and in the last we have the classification layers. So your input goes through these layers, and in every layer there are three basic operations. The first one is the convolution, that is the filtering with the filters, and then ReLU, that is the rectified linear units, they perform the non-linear operation, that is also the modulus operation. all negatives are converted into the positive. And then in the third operation, we go for the pooling. So we have the different types of pooling such as max pooling, average pooling. So here just we are considering, let's say we are talking about the averaging or average pooling. So these operations one by one, I mean the filtering, that is a convolution, nonlinear operation, and the averaging. These similar operations are also performed in the wavelet scattering tree, just we have seen in the previous slide. So there also we have seen the convolution operation where your signal is convolved with the wavelet, and then we find the modulus of these coefficients, and then we convolve these coefficients with the scaling function. Okay, so that is the smoothing or averaging. So the same set of operations are also performed in the wavelet scattering network. So that is the similarity between CNN and WSN, wavelet scattering network. So here we can see in detail. So I have just written the convolution, the nonlinear operation, that is finding the modulus, and then averaging, that means because your psi t is a low pass function. So if you do the convolution with this, obviously you get the averaging of the wavelet coefficients, I mean the smoothing of this coefficient. So these three operations are similar what we generally do in CNNs. So the CNN actually needs training, as we know, so it requires a huge amount of the training data. But wavelet scattering network does not require any training. So in CNN, the filter coefficients keep on updating during the training. But wavelet filters are fixed, that's why they don't need any training. Therefore, wavelet scattering network is faster and can perform efficiently on lesser training data. So WSN uses the complex analytic wavelets, such as one as a Wavelet wavelet, to reduce the amount of the coefficients generated, as we have seen in the previous slide, that every node of the tree is expanding and it is giving the huge amount of the data. So to reduce the amount of the data, we go for the critically downsampling of those data, which is similar to what we do in the discrete wavelet transform, where we downsample the data by 2. So wavelet coefficients, I mean the convolution of f with a wavelet function. So that is the operation, similar operation of continuous wavelet transform. So when these all coefficients are arranged in a specific order, they make a plot, and that plot is known as a scalogram. That's why the wavelet coefficients are sometimes known as the scalogram coefficients. While the scattering coefficients thus arranged, they make the scattergram. So that is the difference. Scalogram means wavelet coefficients, and scattergram represents the scattering coefficients. Later I will show you in the MATLAB that how we can plot the scalogram and the scattergram separately. So now come to the one property of this wavelet scattering transform, and that is time and space invariance. So the features, I mean the wavelet scattering coefficients are insensitive to the translations of the input on an invariance scale. Translation, I'm talking about the one-dimensional signal and two-dimensional signal. So when we create the wavelet scattering network, we specify this invariance scale. I mean we are defining the limit of the invariance, so that within that limit the network or the wavelet scattering coefficients are insensitive to the translations. The support of the scaling function phi t determines the size of invariance in time or space. So later I will show you what is the support. Support means the width of the scaling function. For one-dimensional data, I mean the series, time series, the invariance scale is the duration in the seconds, and that is the width of the scaling function phi t. So if this is your scaling function, then width is the invariance limit. And for 2D, I mean images, the invariance scale is the neighborhood. I mean it's a space of n by n pixels, and that is defining the width of your scaling function. So here scaling function is actually the two-dimensional. Here I should write phi xy in case of 2D. So for example, if you using MATLAB, then by default MATLAB takes 64 by 64 pixels of the width of that scaling function for the image size of 128 by 128. So for the case of images, the features are also insensitive to the rotations. So later I will show you that how you can give the number of rotations per filter. I mean, you can define by default there are 6 rotations. You can increase also. And in this figure, you can see the invariance scale. So this blue one is my scaling function. Okay, so you can see the width of the scaling function, and this width is 2 seconds. So within this 2 seconds, when you shift your signal ft, your coefficients will be will show the insensitivity to the shift. So that is a one-dimensional invariance support. And in case of the 2 dimensions, you can see this is your function, a scaling function, and here this is in the 3 dimensions. So we are talking about the images actually. So here you can see the width of this scaling function is 64 by 64 pixels in this figure. So that is a 2-dimension invariance support. And now let's see how we can define the decomposition label selection. So that I was talking about in the previous slides, that up to the label 1 or 2, it is sufficient to find the scattering coefficients, because the tree is expanding, every node is expanding, so huge amount of the data is generated. So when you go to the higher levels, whether we are getting something or not, so that we will discuss here. So we know that energy dissipates more as we go for higher decomposition labels. So as L increases, I mean the number of labels, L equal to 0, 1, 2 like that, then energy of the Lth order scalegram coefficients and scattering coefficients rapidly converges to 0. So it means the most of the energy is concentrated on the L equal to 0, L equal to 1 and 2. When you go to the higher scattering coefficients, higher level scattering coefficients, they are carrying very less amount of energy. And on the basis of various published results, I mean various research papers, we know that when you go to the third label scattering coefficients, I mean L equal to 3, then their energy can fall below the 1%. So it means up to the L equal to 0, 1, 2, the 99% energy is in those coefficients, and after that it rapidly converges towards 0. So there is no meaning of going beyond the label 3. So for the most of the applications, the wavelet scattering network with the 2 wavelet filters are sufficient. I mean label 1 and 2. Okay, and generally if you want to go further, for one-dimensional signals we can go up to the label 3. But for images, we restrict ourselves to the label 2, because in images, we have seen that tree for one-dimensional. So just imagine for the 2 dimensions where data will be very huge after the third scale, or at the third scale. So we restrict ourselves at the label 2 for images. And now I will talk about the wavelet filters which are used for the convolutions. And what is the quality factor for those? The wavelet coefficients, I mean scalegram coefficients, which are computed by the convolution of signal with the wavelet functions of different frequency. So we have seen that we have performed this convolution. So that is generating the wavelet coefficients. So the wavelet functions are shifted in the time along the length of the signal. So if you are aware that how the wavelet coefficients are computed, you understand that let's say this is your signal and this is your wavelet. So this wavelet is convolved with this function, this ft, and this wavelet is shifted in time. So that means we cover the whole length of the signal. So this is the similar operation what we do in computing the continuous wavelet transform coefficients. So wavelets are convolved and then they are shifted in time. And as I have said that we have the different wavelets, psi 1 1, psi 1 2, psi 1 3, like that. Or what does it mean? It means the psi 1 1 is this wavelet, then which is having, let's say, highest frequency, that the psi 1 2 will be stretched. It is further stretched. So it has the lower frequency. Psi 1 3 will have the further low frequency. So we are convolving the signal with the different wavelets of the different frequencies. Thus, we are trying to capture the high frequency and the low frequency details of the signals at various scales. So that is the basics of the Wavele transform. So similar to the CWT, the shift of this psi t is just one sample in the scattering coefficient. So here also in wavelet scattering transform, this wavelet is shifted on this time axis just one sample ahead. Okay, so that's why we are getting the huge amount of the coefficients also. While in discrete wavelet transform, the shifting is different, but in continuous wavelet transform, the shifting is just one sample. So, but question is that how many wavelet functions we can consider with the desired frequency variations. I mean psi 1, psi 2, psi 3, what I was talking about here. I mean how many frequencies you want to consider for computing those coefficients. So the number of wavelets per octave used for the wavelet filter is known as the quality factor. So quality factor means the number of wavelets which are used for these convolutions. So if I use, let's say, 8 wavelets per octave, what do we mean by the per octave? I think you are aware with that. Per octave is the band of the frequency where the first limit is, let's say, f, then the upper limit is the twice of that f. I mean it is just double. So that is called octave. In decades, the last limit is the 10 times of the initial limit. So the number of wavelets per octave means in this frequency range how many wavelets I am taking for the convolution. That is known as the quality factor. So more number of wavelets per octave will generate definitely the large number of coefficients, and hence the scaleogram will be smoother if you look it. Okay, so but definitely the more computation is needed. So here I have shown the wavelet, first wavelet filter bank, which has the quality factor 8. Quality factor 8 means in one octave we are using 8 number of wavelets. So obviously these wavelets are very close to each other. I mean their frequency variation is near to each other. This is the second filter bank which uses only one wavelet per octave. So I mean in one that band of frequency I'm using a single wavelet. So obviously the resolution will drop here, but this is done because if you see that tree, if you remember that tree where we were computing those coefficients, so at second level the computation is used because every node is expanded in those different wavelets convolutions. So if you take number of wavelets more even at the second level, then huge amount of the coefficients will be generated. So to reduce the amount of those coefficients, we have reduced the number of wavelets in the second level for the convolution. And for images, if we talk about the images, the computation is even more. So we take the quality factor of 2 only. I mean just 2 wavelets per octave for the first filter also. So in case of 1D, we have taken 8 wavelets per octave, but for images, we have reduced this number to the 2 only because of the huge computation. And for second filter bank, we just take the 1 wavelet per octave. Also, we consider the number of rotations per filter bank, and that is equal to the 6 by default. You can also change this in the MATLAB. So now come to the MATLAB implementation of wavelet scattering transform. So we have some functions which you can use. If you talk about the one-dimensional signal, To create the wavelet scattering network, that tree. So that tree structure is first created. So with this function, that is wavelet scattering name value, you can create the tree, and that all information will go to SF. So this is the variable name, you can change it. So let's see the different properties which you can define here in the function name and value pair. So the signal length, this is one parameter which you can define. The default is 1024 samples. Sampling frequency is 1, that is default, you can change it. The invariance scale, which I have just talked, that is the width of your scaling function. So by default, it is just 1/2 of the signal length. If your signal length is 124 samples, then 512 will be the support, the invariance scale. You can change it also. The quality factor we have just talked about, the number of wavelets per filter. So as I'm talking about the one-dimensional signal, so 8.1, it is defined 8.1 for the two labels. So 8 wavelets per octave for first filter bank and 1 wavelet per octave for second filter bank, as we are taking only the two labels. Now boundary conditions means extension of the signal. Extension is needed because we are doing the convolution of the signal with a wavelet function. Okay, so at the boundary, it may be a requirement to increase the length of the signal that is required for the convolution. So you can extend the signal either by a periodic extension of it or by the reflection. So periodic is the default, and precision of the computation double is default, and you can go for single computation also, that will save your memory. And then oversampling factor, and we have the optimization path. These two are the two advanced parameters. Generally they are not needed, but let me explain what is the oversampling factor. So default value is 0, and the maximum value you can give infinity, and in between that you can give any positive integer. So what you do with this oversampling factor actually, so by defining this, you are controlling the amount of the data generated or the coefficient generated in the scattering transform. So if you write infinity, it means the all possible coefficients will be generated and they are undecimated. It means no downsampling is done. So this is exactly similar to continuous wavelet transform. So when you do the convolution of function with the psi, you are getting each and every coefficients, and the wavelets are shifted with one sample, and you are getting the convolutions and lots of coefficients. But when you keep this value 0, then the critically downsampling is done. So to reduce the amount of the data generated. And non-negative integer, if you give some positive integer, depending on that its value, the wavelet coefficients will be generated. So you have the controlling of the amount of the coefficient generation in between 0 and infinity. And now let me talk about the optimized path. Optimized path is slightly complex. So default value 0, that means we are not going for any optimization. And if you keep it 1, then some optimization is done in the network. So just consider this tree. So here every branch is computed. So when you keep 0, this value, then no optimization is done, and then coefficients at every node are computed. But if you keep this as 1, then some optimization is done. Some branches are discarded. So we do not calculate the scattering coefficients for those nodes. And how it is done? It is done on the basis of some frequency or criteria, the bandwidth of the wavelets. So if you are interested in that, you can go through the literature that how the optimization is done and what are those optimization criteria. And now come to the images. So for images, we use this function. Function is same except this 2 is inserted here. So this create the network SF wavelet scattering network for images. And now what we can give the properties for the name value pair. We can define the image size. Default is 128 by 128, otherwise you can change it. The invariance scale is 64, I mean just half of the dimension of this input image. This is similar to 1D where the invariance scale is again just half of the signal length. In the same way, here invariance scale is just half of the image size. You can change it. And number of rotations 6 means this is for first label, this is for second label convolution. So first label the wavelets have 6 rotations, and for second label wavelets also have the 6 rotations. See, we can change this also. The quality factors 1 as I have said, because computation in the images again is very much complicated. So we have reduced the number of wavelets for the convolution. So we are taking just 1 wavelets per octave for both first convolution and the second convolution level. We can also change it. And the computation of precision is single by default, because large amount of data is generated. So to save the memory space, we are representing those data in the single precision. And again, we have those advanced factors, oversampling and optimization path. So their meaning is the same as in the case of one-dimensional signal. So now come to the MATLAB implementation of one-dimensional signal. So how the wavelet scattering coefficients are computed. So this is the function scattering transform. Okay, in the previous functions create that network structure, I mean the tree. And this network structure is passed to this function SF, and this is your signal. So when you execute this function, you get two variables S and U. So here S captures all the scattering coefficients, and U captures all the wavelet coefficients or scaleogram coefficients. So here SF is wavelet scattering network, which was just defined by this function, which we have already seen in the previous slide. So we can plot the scattergram and the scaleogram also. So as S is carrying all the scattering coefficients, U is carrying all the wavelet coefficients or scaleogram coefficients. So with the help of this S and U, I can plot the scattergram and the scaleogram. So this you can plot at after the certain filter, I mean after the first label or the second label. Not all can be plotted simultaneously. You can plot one by one. So here this is the command scattergram. The command is common for both scaleogram and scattergram. So scattergram SF is that your wavelet scattering network. When you use S, your scattering coefficients will be plotted. And when you use U here, your wavelet coefficients, I mean scaleogram, will be plotted. And here you have to define the filter bank and 1. It means after which filter bank you want to plot these coefficients. So when I write filter bank 1, it means after the first convolution, the coefficients will be plotted. If I write 2 here, it means after the second filter bank, the coefficients are plotted. So for images, the same function is used, a scattering transform. Okay, so this is my image. In previous case, it was my one-dimensional signal. And this is your network, wavelet scattering network, which is defined by already by wavelet scattering 2. And here we cannot plot those scattergram and scaleogram because of the complexity of the two-dimensional. So here after executing this function, you get S and U. Again, S will carry all the scattering coefficients and U will carry all the wavelet coefficients. So here S is the cell array. Okay. So if decomposition labels are, let's say L equal to 0, 1, 2, these are 2 labels, then we get 3 cell arrays as S1, S2 and S3. So S1 will carry only the scattering coefficients of 0 order, I mean L equal to 0. So as we know that L equal to 0 contains only the convolution of your signal and scaling function. So S1 cell array will include only the convolution of your image and the scaling function. So as we know that scaling function is a low pass filter, So convolution with the image definitely will give you the blur image. I mean, if you see those coefficients, it is just blurring of your image, right? So now come to the program. So here I am finding the scattergram and the scaleogram for an ECG signal. So I'm loading that ECG signal. It is inbuilt in the MATLAB. So just by load command, you can load it. And the sampling frequency is 180. So my ECG signal goes into the X variable. This code I have written for selecting my own signal. Here I have used the MATLAB inbuilt function for selecting that ECG signal. But if you enable this code and disable this code, you can select your own one-dimensional signal. So here I have written this code for selecting an audio file. So here you can see that when you execute this code, a system dialog box will appear, open dialog box, and from there you can select your audio file. So you can select any of your audio file, MP3, wave, whatever. And here I am checking whether this selected audio is stereo or mono, because I need a mono audio. I mean the single channel audio for the computation, not the double channel. So if it is double channel, I mean stereo, then I'm converting this into the single channel audio. With the audio read function, I'm reading that signal. So the audio goes to the X and the sampling rate goes to the FS. So if you want to select your own audio, you can enable this code and you will disable this code. So that I will show you in the MATLAB execution. And here I'm initializing the tree SF with the wavelet scattering, as I have discussed in the previous slides. I am defining the signal length. Signal length is the length of the X which I am reading. Sampling frequency is Fs, which I am reading from the signal. And now with the scattering transform, I am getting the coefficients. So this tree structure is passed. This X, which is your audio or ECG signal, is passed here. And all the coefficients, scattering coefficients will go in as, all the wavelet coefficients will go in U. And with help of the scattergram, I am displaying the S, I mean all scattering coefficients, and with the U, I am displaying all the scaleogram, I mean the wavelet coefficients after the filter bank first. So when I execute this, you will get two plots. One is a scattergram, another is a scaleogram. So let me take you to the MATLAB. Okay, so this is my MATLAB and this is my editor. So this program is already written here. And here I have taken the ECG wave. So I'm just running this code, and you will have the two plots. Okay. So this is this one is the scaleogram coefficients after the filter bank 1. So these are all your wavelet coefficients, right? And this is your scattering plot. So here you can see all the scattering coefficients. So as we know that how we get the scattering coefficients we get by the convolution of the scaling function. So these wavelet coefficients, okay, they go to the modulus operation, and smoothing is done by the scaling function phi t. So you can see that this scattergram is more smooth because of that phi t convolution. Okay. So now I will show you that how you can choose your own one-dimensional signal. So I will disable these commands, so making them comment, and then I'm enabling these commands. So just uncomment them. Okay. So now when I execute it, it asks me to choose my function. So I can choose my audio. So I have different audios. So I'm taking the flute. It's a flute audio of 10 seconds. So when I run it, okay, so this execution is complete, and here you get the two plots. So in this, this is a scattergram representing scaleogram coefficients. So these are all wavelet coefficients. You can see, let me enlarge it. So these are the wavelet coefficients you can see. And the second one is showing all the scattering coefficients. So these are the scattering coefficients after the filter bank first for that flute audio. So this is about the one-dimensional signal. Now come back to the presentation. So let me discuss the code for 2 dimensions for the images. So here with this I am selecting my image. So I am selecting the grayscale image. So that image goes to IMG variable, and then this image is plotted. And now I define the wavelet scattering network with the wavelet scattering 2 function. Image size is 256 by 256 and invariance scale is 28. I'm taking 28. If you don't define it, this will be just half of it, that is 128. But I'm taking 28. And with help of the scattering transform, I'm getting all S and U coefficients. So this tree, this SF structure is passed here, and your image is also passed here. So all the scattering coefficients will go in S, all the wavelet coefficients will go in U. So now what I am doing here, I am, as I said, that S has 3 cell arrays, S1, S2 and S3. So as I said, that first cell array will include the convolution, the coefficients which are obtained by the convolution of image and the scaling function. So obviously, as I said, that scaling function is a low pass filter. So you get the blurred image. I mean, all coefficients will represent a smooth image. So I'm getting those coefficients. So S1 dot image is 1 1. It means all those F convolution phi t, they are low frequency coefficients because of the smoothing, so they all go to the S1. And because of the downsampling, their size is small. I mean, I get a small matrix instead of 256 by 256. Although my image size was this, but because of the downsampling of the coefficients, this matrix size is small. So I am stretching again it to the 256 by 256 so we can visualize it better. So with the IMD size, I am taking back to the 256 by 256 and then showing these coefficients. Okay, so here you will see the blur image, and now getting the wavelet coefficients from the U. So at label 1, total coefficient matrices are 18 with 3 different wavelet resolutions. Why 18? Because it has used 3 wavelets, psi1, psi2 and psi3 for the convolution. Okay, and each has the 6 rotations. So total 3 into 6, 18 different convolutions will take place. So total 18 matrices are obtained at the label 1. And similarly at the label 2, total coefficient matrices are 108. So you can see that how the tree is expanding at every node. So with this code, I am extracting the wavelet coefficients from the U. Okay, all those 18 coefficients, and those all 18 coefficients are going into this cell array CU. And then I am displaying those here with this command. And here I am taking the scattering coefficients from the S. So with the similar commands, I am getting all the scattering coefficients after the first filter bank, and they are going into the CS. I'm not going into the second label because there are total 108 matrices. So it will be difficult to show them on the screen. And at the label 1, I am getting since only the 18 matrices, so that I can show. So with the first section, I am getting all the U coefficients, means wavelet coefficients. So I will get the total 18 matrices. They are having the wavelet coefficients, and with this section, I am getting all the scattering coefficients and all 18 matrices here. So now let me run this program in the MATLAB and show you all those coefficients. So this program I have already written here, the same program. So I will just run it. It will ask me to choose the image. So I have these 4 grayscale images. So I am choosing this pepper image, pepper.jpg, and let's see what happens. Okay, so in this figure, I'm just displaying my image. Okay, this is my input image. So let me close it. And this is what I was talking about, the blurred image. That is the obtained from the zero order scattering coefficient. So this is the result of just convolution of my image f with a scaling function phi t. So I have taken the support width of 28 pixels, if you remember the code. And just because of taking the 28 pixels, I'm getting this type of blur. If I take the width size more, I mean, if I take, let's say 128 pixel support width, then obviously I will not be able to see these peppers, which I'm seeing in this case, because when the window size is more, the more blurring will take place and nothing will be visible, just a blurry background will be there. Just to show the difference between the original image and this, that how blurring is taken place, I have taken that number 28. Otherwise, the default you can take that is the invariant scale of just half of the image size. And now let's see the another plot, this one. These are all the wavelet coefficients. Okay, so total 18 images are there. As I said, the total 3 wavelets are used, psi1, psi2 and psi3 by the MATLAB, and each has the 6 rotations. So for psi1, you have total 6 images. You can see 1, 2, 3, 4, 5 and 6. And for second wavelet, again you have 6 images, 1, 2, 3, 4, 5, 6. And for third, psi3, you have 1, 2, 3, 4, 5, 6. So in first image, first 6 images, you can see the effect of the rotations of the wavelet. So when you see the first image, I mean the wavelet coefficients, you can see that the vertical edges are more prominent, right? So it means this wavelet with this particular rotation is capturing or highlighting the vertical edges. And if you see this image, this one, so here all the vertical edges are completely eliminated. So obviously this wavelet will have the different orientation. So it is not capturing those vertical edges. So with different rotations, we are getting different edges which are highlighted in these images. And now let's see the scattering coefficients. So these are the scattering coefficients. So again 18 matrices. So for psi1, those wavelet coefficients are convolved with the scaling function phi t. So 1, 2, 3, 4, 5, 6. So those first 6 images are first modulus is taken, and then we convolve them with a phi t, and then we get these 6 images. So these first 6 images for psi1, and the next 6 slot is for psi2, and the last 6 images for because of the psi3. So 3 different frequencies are used here. And this is for first level convolution. As I said, in the second level, we got the 108 coefficient matrices, so it is not possible to show you them. Okay, so this is all about this video and what I have covered. Let me summarize. So we have gone through the basic theory of the Wavele Scattering Transform. We have seen that how we can compute the scattering coefficients for 1D and 2D signals. We have seen the similarity between the CNN convolutional neural networks and the Wavelet scattering network, and we have seen the implementation in the MATLAB for both 1D and 2D signals. So I hope you have enjoyed this video, and the wavelet scattering coefficients which we have obtained in this video, we can use those coefficients as features for the signals and images, and they can be used for classification task. So in the next video, probably I will come with the implementation of some classification of signals or images. So thank you very much for watching this video and giving your precious time. I hope you have enjoyed it and you have liked this video. So you can share this video. So in the last, thank you once again. Have a nice time.